Hello and welcome back to this course on programming in Rust. In this video we're going to build a small key value store similar to Redis that clients talk over a network connection. It will serve lots of clients at once using a pool of threads. It will keep all of its data safely behind a lock, and it will be able to shut down gracefully when we stop it. So we're building a server that's going to listen on a TCP port. Clients will connect and they will send simple text commands. They'll send set to set a key to a value, get to get the value for a key, or delete to delete the key. Behind the scenes, we're going to use a shared hash map to hold all of the data and a fixed pool of worker threads to handle all those connections in parallel. Finally, when we stop the server, it will finish any in-flight work before it exits, instead of dropping the connections mid-request. Okay, so I've already gone ahead and created a new project called key value store. And again, I'm going to create a lib.rs file because we're going to use this as our library and keep our main really thin. So the heart of the server will be the run function. Essentially, we need to listen on a port, create the shared store and a thread pool, and then land every incoming connection off to that pool. So here we're going to define the thread pool and the connection handler. Okay, so bind is going to open the port, and incoming gives us each connection as it comes in. For each one, we're going to clone the store handle, and then we hand a closure off to the pool, which then runs it on a worker thread. And I'll actually write the code that we're going to write in our main function, in our main.rs. So I will come in, import run, don't forget semicolon, and we'll go run, and I'll just point it at the address that we'll run our server on. Even though we haven't quite finished it yet, port 7878. There we go. Now let's take a little bit of a closer look at this store. It's a hash map that every worker reads and writes. So it uses the same Arc and Mutex pattern that we use for shared state. The Mutex gives one thread at a time exclusive access, and the Arc lets all workers share ownership. And we gave it a short type alias, store, up at the top in our lib.rs file. So every worker will get a clone of this Arc with arc -- clone, or clone, sorry, so that they all point at the very same map. Now let's go and work on the handler so we can pass a command and response. This handler will read the connection one line at a time, and for each line, it will spit off the command word and its arguments. It will match on the command, and then it does the operation under a quick lock, and then it will write a reply back to the client. So I just need to add a couple of more using statements at the top. And then underneath the run function, let's write the following. Okay, so this match is sort of working like a match on an enum that we looked at earlier in the series. Except here we're choosing what to do from the command word. So we've got one for set, get, and delete. The let else line above here is also doing a bit of pattern matching as well. If a line can't be read because the client has disconnected, we stop. And notice one important thing about the lock. We only hold it for an instant when we read or change the map, and then we let it go before writing the reply. So one slow client can never block the others. So spawning a brand new thread for every connection doesn't scale because threads are not free. So instead, we're going to build a thread pool, a fixed set of worker threads that pull jobs off a shared channel. So I'll add a couple of using statements for this. We'll introduce a new type. We'll create a struct for a runner. And we'll create our struct for our worker pool. And then finally, we'll create an implementation for our worker pool. All right, so a task is essentially a box closure that's send, which essentially means it can move to a worker thread. In our new constructor, we make one channel, scrolling off the screen there, and we wrap its receiving end in an arc and a mutex so workers can share it. Then we spawn the runners here. And each runner loops. It locks the queue and then pulls the next task with a let else, which releases the lock before the task runs. And if the channel has closed, the let else breaks the loop, and execute boxes the closure and sends it down the channel. So this one thing ties together channels, arc and mutex, and the box and trait objects from smart pointers that we talked about earlier in the course. Finally, we need to perform a graceful shutdown instead of killing the threads mid-request. And we're going to do that by implementing the drop trait for the pool. Still in this file, so we'll do it underneath the implementation for worker pool. So when the pool goes out of scope, drop will run. It will drop the dispatch sender so no new jobs can arrive, and then it joins each runner so that any in-flight work will finish first. Okay, so this is the drop trait from smart pointers doing its cleanup, and it will run on its own when the pool is destroyed. There is one catch. For our demo, our run loop never stops by itself. It can accept connections forever. So normally this cleanup only happens when we stop the whole program. If we wanted to test this a little bit, we could cap the loop with a limit on the incoming listeners. So for example, we could write listener.incoming.take 3. So it stops after 3 connections. Then run will return and the pool will go out of scope, and then you could watch the drop tidy everything up. But for now, that's just a mental note. Okay, let's go ahead and run this. So I've opened a terminal and I've split the terminal. So in this one, we're going to run our project. Okay, so the key value store is running. So now I'm going to talk to the server using ncat or a netcat compatible CLI. So 127.0.0.1, and we're on port 7878. Awesome. So I'm in this key value store now. So let me go ahead and try and set a key with the value will. And then I'll try and retrieve that. That was successful. Let me try and retrieve something that's not existing in the key value store. Awesome, that works. And then let me go ahead and delete that name. And then if I try and retrieve that, again, it's not found. So there we go. We've built a basic key value store in Rust, kind of like Redis cache, which I think is pretty cool. That's a really awesome thing that we've built there. If you wanted to go further, you could add an exists or a keys command. We could persist the map to a file on shutdown, so when we start the key value store again, it would still have those same keys and values in there. Or you could give entries a simple expiry time. Each one of those is just an interesting way how you could expand this a little bit further. But for now, let's recap. So in this video, we built a key value store using Rust, essentially a Redis clone. We built a program that could accept TCP connections, so the server listens on a port and answers a small text protocol over each client connection. And this is real network programming that we were able to do without a framework, and we built everything using the Rust standard library. We built a map that we could share using Arc and Mutex. So one hash map lives behind Arc and Mutex, so every worker co-owns it and only one can touch it at a time. We learned how we could serve many clients using a thread pool. So we created a fixed pool of worker threads that pulls jobs off a queue instead of spawning a fresh thread per connection forever. And we also learned how to shut down gracefully with the drop trait. So when the pool is dropped, its drop code stops the workers and waits for them to finish so that no thread was abandoned in the middle of their work. Now, this was the final video of a planned series. If you've gone all the way from installing Rust to shipping real concurrent programs, congratulations. Along the way, we talked about ownership and borrowing, structs, enums and pattern matching, generics, traits, error handling, iterators, smart pointers, concurrencies, and asynchronous programming. We also built a game, we built an interpreter, a couple of command line tools, a fractal renderer, a web crawler, a key value store, and we also built a WASM particle simulator. So where to from here? I recommend you go and look at the official Rust book. The link to that is in the video description below. Pick a project that you care about and go and build it and try and contribute to an open source Rust crate. You've got the tools now, so whether you want to write the code yourself or get an agent to do it, you now have the tools to be a proficient Rust programmer. And the best way to keep learning is to keep building. If there is a project that you'd like to see being built in Rust, pop it in the comment section below and I'll add it to my video backlog and we'll try and create a video on how you can actually build such a project in Rust. But to finish for the final time, thank you so much for watching this series. If you like the video, give it a like. If you want to see more videos from me, don't forget to subscribe. If you have any questions, pop them in the comment section below. Thank you so much for watching and we'll see you all next time.